Good morning, this is the heat pipe project for ME412 Heat Transfer Laboratory. This is the Spartan Dawgs team composed of Dan Schwartz, John Tyhe, and Darius Barrett. This slide serves as a brief introduction to heat pipes. The purpose of a heat pipe is to transfer heat between two interfaces. A heat pipe is a sealed pipe with a working fluid inside. There are two main sections of a heat pipe, the evaporator and the condenser. In the evaporator region, heat enters the heat pipe, heats up the water or working fluid. The working fluid absorbs the energy and vaporizes. The vapor rises to the top of the heat pipe, cools off, releasing heat, and condenses back into a liquid and falls back to the evaporator region. The experiment today will utilize a heat pipe to cool 1 liter of boiling water. This is the heat pipe created by the design team. There's both the evaporator and condenser region, as well as an insulated CPVC midsection. The insulated section is meant to reduce heat transfer in this area and allow the water vapor to reach the condenser region to release heat. The operation process for getting the heat pipe ready for operations is as follows. Seal the working fluid in the heat pipe by putting it in the evaporator region and closing valve 1. The next step is to use the vacuum pump to lower the pressure of the pipe. Hook up the vacuum pump to the male hose connection and open valve 2. Turn the vacuum pump on and evacuate the pressure from the heat pipe. After this has gone on for a few seconds, close valve 2 and disconnect the vacuum pump. Now you can open valve 1 and the heat pipe is ready for use. Both the evaporator and condenser regions were made out of copper, a highly conductive material to promote heat transfer. The heat pipe was modeled in such a way to predict what temperature the beaker of water would be after 15 minutes of time. The general approach involves solving for the heat transfer rate, the maximum heat transfer rate of the heat pipe using equation 1. This maximum heat transfer rate equation doesn't take into account resistances. The resistance network for both the evaporator and condenser region were determined and used in equation 2 along with the temperature gradient to find the rate of heat transfer possible in these regions. The heat transfer coefficient was calculated using the Nusselt number correlation for the free convection on a heated vertical plate. The results of modeling concluded that the heat pipe was capable of reducing the 1 liter of boiling water in 15 minutes by 13 degrees Celsius. This is shown in the table below. Some testing was conducted and the results are shown here. Table 1 is the control experiment. In the control experiment, 1 liter of boiling water was poured into a beaker and temperatures were recorded at the initial 7.5 minutes and 15 minutes. In 15 minutes, the 1 liter of boiling water cooled to a temperature of 69 degrees Celsius. Table 2 involves the experiment with the heat pipe. The working fluid in this case was water and a volume of 30 milliliters. The initial temperature was 90 degrees and then the final temperature after 15 minutes was 67 degrees. From this, a conclusion was made that the heat pipe contributes 2 degrees Celsius of temperature change to the 1 liter beaker of boiling water. Future recommendations involve constructing a more comprehensive model to accurately describe the heat pipe. Further investigation on the height of the heat pipe is needed. The team felt that the vapor wasn't reaching the condensing region and was instead condensing in the CPVC region, which has a high heat transfer resistance, and also to experiment with different working fluids. Thank you.